Welcome back. A little bit less stress today, right? So as far as the exams, I will work on them. I've got 2 classes worth to score. I'll be working on them probably starting Friday, and I will get them done over the weekend. As I score them, I enter them, but I don't release the grades, the scores until everybody's in there. Otherwise, well, it's just make it fair. Okay, so those will be coming. I'll see if I would like to be able to do the same thing where I post the PDF, so when you see your score, you're able to see it. I got to just get the timing so I can do it in a reasonable amount of time. Last time it took almost 20 hours. So I think I can get it set up to take up less. So what I want to do is update us where we're at. And in a sense, we really don't have any new material. We are going back over the material we've already learned, but we're doing it backwards in a sense. So let's see, we're exam 2. So now we've got 13.1, 2, 3, 4, and then 14.2. You'll see in the modules I have 14.1, so they've changed they got rid of 14.1. So we'll pick this one up. But that's not too much content. And then after that, we have 3 sections. And sometimes we'll see, I'll get the official word whether 14.5 will be on the final or not. But the final will be comprehensive, and it'll pick up these last 2 or 3, whichever ones they decide. So this is a period of time where it's a good time to start reviewing the stuff that was on test 1 and 2 as we get into this, because it's actually going to be helpful, because we're really doing what we did in 2 and 1, but we're doing it backwards. We're starting with the answer and we're getting back to the question. So it's like a math Jeopardy in a sense, right? We're looking for what the question was. The thing we do pick up is that the description of what we're getting is a little different, right? What did we call it when we took a derivative? What did we end up with? A rate, exactly. So a rate, the speed at which something was happening. Rate of change, instantaneous rate of change. So that's what we ended up with. So let's just think it through. Well, it's in there sort of. But if we start with a rate and we go back to the original function, what are we going to have in that original function? It's no longer a rate. We started with a rate. We know how fast we're going. What would we get when we go backwards? A little bit harder to think about. We will get a value. And actually what we're going to get is, because that happens over time, we will get an accumulation. So if we were traveling, it would be how many miles we traveled, right? We know our speed. We're able to calculate how many miles we traveled. So it's the accumulation of stuff. Our boat is leaking, unfortunately. Over time, again, if we know the rate that the water's coming in, we know how much time has passed, we will know how much water's in our boat, whether it's going to sink or not, maybe. So that's the kind of thing that we're getting. So just think, we're starting with the rate and we're working backwards. How many times does that happen? Quite a bit. A lot of times we know how fast things are happening, how quickly, how many dollars per hour people are spending in our store. That will allow us to come back and say, what's the profit going to be over time? Okay, so this is another powerful tool. And again, the way we're going to do it is really just backwards, and that's how I'll introduce it. And so we'll do that today, the indefinite integral, and then you'll just keep seeing there's definite integral, numerical, graphical. Here's definite integral, algebraic. So really the same thing again with 2 different versions, doing it from a graph, doing it from a formula. And also what we end up with is what accumulates is the area. So we'll talk about that. And then substitution is going to be a technique we use to get back to something that came from a chain rule. So today we're going to go with, I hate to call them simple, but one-step derivatives, the simpler ones. Something that comes from the chain rule is a lot hard. It's harder to spot what it is, and it's harder to go backwards, right? It was harder to do. So that's what we'll use. Substitution will give us some tools to go backwards when our derivative came from the use of the chain rule, because that's sometimes hard to see. But otherwise, today we're just going to go with an introduction and go from there. Okay, let's see, here I am. Okay. And so I opened up the test 3 modules. I took the dates out. I'm still kind of updating them, so this is, I think, probably left over from spring semester because I just copied them over. Notice it's got section 14.1. That's not even in the syllabus, so I'm working on these, but 13.1, I did review the slide deck. We're going to be good. We're set up. I've got a previous semester's lecture recorded. Might even gone back to the pandemic time when we were on lockdown, but we will go through. So what we call this, instead of a derivative, we call this an integral. So when you see the word integral, we are integrating, which means we're taking the underderivative. They call it the antiderivative as well. And then so we're going to call this an indefinite integral, and you'll see just kind of to pinpoint it, when you take the derivative of a function that has a constant, like plus 5 on the end, what happened to that plus 5? Derivative of 5 is 0. So when you go backwards, you don't know whether that's 5 or 100, because once you take it and it becomes zeros, there are some ways to find out. We'll see that we'll do it. But in general, we don't know what that constant was. We've got all these techniques, we can get the function, but unless we have some additional information, we will not be able to get that constant. Okay, so that's why we call it indefinite. It's really, we get a family of integrals that, we get a family of functions that would fit. Okay, so antiderivatives and the indefinite integral, really those again are two words that give us the same thing. An antiderivative is indicating that what we start with is the derivative. So again, it's starting with the answer that we've been trying to get at with everything we've done, and we're going to go backwards. We will also call that same process the indefinite integral. Okay. So what do we know about derivatives? Let's think this through a little bit. Let's start with maybe one of the early derivatives that we started with. Shoot, I keep forgetting to have my pencils ready for me. Okay, that worked. Okay, so I'm going to start with a function. Let's go with, let's just do something easy. X to the third. Oops, just x to the third. So if we have our function is x to the third, what would be the derivative of this function? 3x squared, right? Let's do it a little slower. Let's kind of go slow motion, all the pieces. So we have this. What's the first thing we do? The first thing is we bring the 3 down. Let's see if I can make a dashed, I can't really do a dashed line 3, so we'll put the 3 in red. That's the first step. So we'll leave that first. Because remember, when you're going backwards, not only do you do things backwards, but you do it in the reverse order. Okay, so that's the first step. Second step was to subtract 1, right? So here's our second step. We're going to subtract 1. Okay, and that's how we got the function 3x squared. We've been doing that, right? Let's see. Again, you're going to see, I think you'll pick this up pretty quick. If we want to integrate, and so I'm introducing the symbol before we get too much into it, but that's the integration symbol. if we want to integrate this derivative, and we'll put the dx there to indicate that that is a derivative. So this is all the formatting. When you do questions, you'll see this little s for integral. It's actually coming from sums. 3x squared dx. Dx means that was a derivative. So we want to get an antiderivative. We want to get back to the function. We kind of know what we got here, right? We better end up with that because that's what we started with. We got the derivative. That's all the integral is going to do for us. But let's think of the steps. What are the steps we're going to do? We're going to do the opposite steps, opposite operations in the opposite order. So what was the last thing we did? The last thing we did to the derivative was subtract 1 from the exponent. What would be the opposite of subtracting 1 from the exponent? Got it. See? Simple. We just do the opposite. In fact, that's what I say in my algebra class. If you were a little bit rebellious when you were a teenager, and who wasn't, right? Your parents said do this, you did that. They said yes, you said no. Whatever. You'll be good at this because everything we're doing is backwards. So we're going to start with the 3x squared, but the first thing we're going to do here is we're going to add 1 to that exponent. So that's our first step. So that was our first step. So that was the second step there. If we go back, what was the step before that? We took the exponent and we put it down in front and we multiplied. So what are we going to do now with this new exponent of 2 plus 1? We're going to bring it down and divide. Exactly. Opposite of multiplication. That's all there is to this. So we're going to divide by the new exponent because, again, we're doing full order of operations, but we're doing it all backwards. So what do we end up with? We end up with 3x to the third power over 3. The 3 divided by 3 cancels. We end up with x to the third. That's exactly what we started with before we took its derivative, right? So do you see how this is really just a backwards process? So you'll get some practice taking derivatives, maybe going back and reviewing. This is a great place to start reviewing especially if you didn't do as well as you'd like on the 2 previous tests. You'll review, you'll learn it, and it'll show up in the final exam, and you'll still do well in this course, okay? Get all that homework done, and it should all be open. If it's not, let me know, and I can make it available, but we can get you all the points on that by practice. But notice it's just opposite of what we did. Instead of subtracting 1, we're going to add 1, and instead of multiplying by the exponent first, we're going to divide by the exponent second after we made the new exponent. That's all there is. And it gives us that. Now, we don't know. We could have started with the function being x to the third plus 8, right? Or plus anything. We would have got the same derivative because the derivative of 8 is 0. We still would have ended up with 3x squared. And so notice that we would, when we integrate this, integral of 3x squared dx, we will also get x to the third, but these are 2 different functions, aren't they? One is x to the third, one is x plus 8. So actually we could think of that as x to the third plus 0, really, right? Same thing. We could put this. So when we do this integral, this indefinite integral, we always said, oh, there might be a constant out here. We're not sure. Oh, I didn't. This is should be a 3. There might be a constant out here. So in this one, you should remember to always, once you get your answer, put a plus c, because we don't know. So that gives the whole families of what it could be. Okay, and it's specifically because whenever we have a constant, you take its derivative, that disappears. We don't know what it is. We'll look at an example where we'll actually be able to find out what c is, but for now, we'll just do that. So far, so good? So let me give you 2 a little more challenging ones. So that's anytime we're taking the derivative of an exponent, of x to an exponent, right? Which is the most of the case. But there were two other types of exponents we took, right? Another x type was exponentials. E to the x, right? When we took the derivative of a exponential, what did we get? Take its derivative, we get e to the x. Doesn't look like anything happened. So when we integrate e to the x dx, what are we going to get? Exactly what you're thinking, but you're afraid to say it, because it seems to be so e to the x. Technically plus a constant, because we don't know if there was originally a constant or not. But so this one it's harder, but it's easier at the same time, right? It's harder because it just doesn't seem, well, it doesn't look like I did anything. So with e to the x, it is. Now we'll get a chance to look at if it was some other base, but we'll deal with those specifics. But I just want you to see that we're going to need to remember how that this derivative, it's its own derivative. So when we integrate it, it's its own integral too. So it's kind of cool. This next one is the other one. So we'll do this h of x. When we had the natural log of x, what was that derivative? Good, 1 over x. Exactly. So we just had to kind of remember, I mean, when we talked about it, we just said it is because it is. And mathematically, to kind of show why that works, takes a couple pages and a couple tricky things, and you still won't understand why. I don't, at least after all these years. Probably a little bit, but okay. So that's its derivative. So when we see an integral that starts with 1 over x, or x to the minus 1 power, right? Remember, we're just going back to where it came from. The best way is to remember that this works this way, so all we're doing is going backwards. What's the derivative? What's the integral going to be? ln of x, right? The natural log of x. These are ones you're just kind of going to have to remember. Just like, and I guess we could put absolute values here, and the only reason we do that is because x could be a negative number, right? And you can't put negative numbers into the natural log. So we do that. But I missed one thing, plus a c, because there could be a constant. So we're thinking, remember, whenever we take an integral, there's all that possibility that there was some sort of constant in the original function, so we indicate that with plus a c. Until we get to what we're going to call the definite integral, and we'll see how that all works. But these are basically the three things. If those things seem pretty good for you, you're going to be just fine. So anything with an exponent, we're just going to add one first, and then we're going to divide by the new exponent, right? Up there. If it's an exponential, at least using just the e in business, that's typically what we end up using. It's its own derivative, so it's going to be its own integral. So you're going to get, you're going to see that. And the natural log is going to be 1 over x, so when we see 1 over x and we want to integrate it, we're going to go back to the natural log. So it's just kind of, and those will be all the types of integration we're going to need to be able to do. Again, we'll throw in some, because remember, these got a little complicated. If the exponent wasn't just x, if it had a function inside there, we have to do the chain rule, and going backwards on the chain rule can be difficult. However, it's going to show up in the integral. You'll see it, okay? But we'll also get some tools that'll help us to see it if we don't see it right away. Okay. Basically, we just did the whole lesson, but I'm going to keep going through here. We'll do a few examples, but that's it. So they call it an antiderivative of a function. F, little f, is a function big F, such that the derivative of big F is little f. Again, sometimes what they're doing is just saying, I'm not sure what they're saying here. the antiderivative of a function f. So basically they're saying we're starting with the derivative function, little f, and we want to get back to the function big F, because big F, if you take its derivative, you've got little f. So little f is the derivative function. Okay? And so another way showing what we've done is that big F is equal to the integral of little f of x dx. Okay, so little, in this notation, little f is the derivative already. We're trying to integrate back, we'll get the big F. Okay, so same thing we were doing, just some math notation. So they take a quick look at, they went with x to the third, starting, and again, saying that 4x to the third is the derivative. So what would be the antiderivative? Let's just walk through this. How do they get there? They add 1 to the exponent, and then they divide by that new exponent. I'll write it this way, 3 plus 1. Remember I told you at the beginning, if you can add 1 and subtract 1, you can do calculus. That's all we're doing in calculus. Now we're doing the addition part. We've been doing the subtraction part all along. So 3 plus 1 is 4, so 4 divided by 4 is 1. 3 plus 1, yeah, it's x to the fourth. Again, they haven't quite got there, but the function we would put is plus a constant, because if you take a derivative of a constant, it becomes 0, and it gets lost. And then again, I wouldn't spend too much time, but I left it because of textbook. So if the derivative of a of x is b of x, so b of x is the derivative, then b of x is the antiderivative of a of x. Then an antiderivative of b of x is a of x. So if you take a derivative, integrate it, antiderivative, you get back to where you started. So, and we call that an indefinite integral. Indefinite because of that plus c. We don't know exactly which one, but it could be an infinite number of things, because c could be any kind of a number, right? Doing good so far? Not too bad. Again, we'll look at examples here. I think start. So now they're going to just introduce the notation, which I've already done, sort of spoiled it, right? You get this little squiggly line, looks kind of like a musical note or something, but it's sort of for an S. I don't think we get into, one of the ways they figured out how to integrate was they actually took a sum. I think we do it towards the end. You'll see we can do it with summation. So that's kind of a fancy S for integration. Again, we start with a function that is a derivative. So it is a rate of change. It's a speed. It's something like that. And what it's asking us to do is take the antiderivative, derivatize it, whatever word we want to use, right? We're just trying to get back. And so you'll see some words, function f that is being integrated is also called the integrand. I don't use language too much because it all confuses me, so, but it's here if you read it in a book, so that's the integrand. It's the derivative, right? I just want to see it. It's a derivative. We're trying to get to the underderivative. And so they give the example down here. And again, this is the same one we did on the other page, just in really nice notation. And they say we have this plus c because it includes every form of this integration, because we could have an infinite number of different constants there that when we take its derivative, they all become 0. Yes?
It confuses like why, because I have the same like problem on the homework one right now.
Uh-huh.
Why do you divide?
Why do you divide? Okay.
Like I give you the homework one I just did.
Sure.
It's 12x to the power of 7.
And they want you to integrate it, right? Best way to figure it out is once you get your answer, take its derivative and see if you get back to where you started. then you'll see, because not only do you go backwards what we've been doing, but if you take the derivative again, you'll be going back and forth and back and forth. You'll see it. So that's good timing. So if we integrate this, what are we supposed to do? We're supposed to add 1 to the exponent, and then we're supposed to divide by that new exponent. And then we get this constant. So actually I should put the dx there, right? So you're going to do something like this in the homework. So you end up with 12x to the 8th power divided by 8, which, okay, it seems completely different, right? You could reduce it, but I'm not going to do that quite yet, because 12 and 8 both have a 4 in there, so that, well, why don't we go ahead and do it? Plus a constant, but 4 goes, so that gets 3x to the 8th over 2. And again, we've lost some things, and then we could put plus a constant. That might be the answer that they're looking for. But what I would do is I'd come right here. Let's take the derivative of 12x to the 8th over 8. Okay, so now we're going to take a derivative. I'll do it this way. We're going to take the derivative. What's the first thing we do when we take a derivative? Bring the exponent down. So the 8 comes down, and we're going to multiply by 8. What's the next thing we do? Subtract 1. Okay, so speak slow enough and somebody will catch up on me. So subtract 1 from the exponent. So watch what happens. 8 divided by 8, they cancel. We get 12, 8 minus 1, x to the 7th. Isn't this what you gave me, right? We got back to where we started. That's why we have to divide by the 8, because it's going to come down, and so it's taking care of that.
Do you only put the plus C equally after everyone?
You should. This is one of those things I always forgot, and since I was a math major, I'd lose points. My head teacher, okay, you didn't put the C, minus whatever. I won't do that, but just remember it should be there. A lot of times in the web assign, they have the plus C already sitting there. Sometimes they don't, and they'll say it's wrong, and you go, wait, I know it's right. You forgot the plus C, okay? But it's conceptually it's there, but it's not as big of a deal as, because we can't do much, right? So, yeah. But see, that's why I particularly don't care for simplifying too much, because if we don't simplify, it's a lot easier to see where this came from, or how to get back, right? With the 8 in the denominator. But they have us do this. Does that make a little sense? This is cool because it also tells us once we integrate to check our answer, kind of like algebra when we were solving, we can basically take its derivative and see if we got back to where we started. That's a technique we're going to use on Monday when we're doing the substitution, because it's more complicated. We're not quite sure if we got the right thing, so we'll take its derivative. And in that process, if we don't have the right answer, usually we'll be able to figure out what we left out. Okay, so get early on. If you'll do this, take its derivative, and then integrate it, get its antiderivative, but then take the derivative again and see if you get back to what you started with, and you'll see where all the pieces happen. All right, good question. The constant of integration, C, reminds us that we have to add any constant and get the antiderivative. That's all it is. It's a reminder. It's not really that important. Although every mathematician will tell you, no, it's critical. The world will fall apart if we don't put plus C. But the world will do just fine without plus C. Okay? So again, this is where they're giving us set up is check the following. So they give us the answer, they integrate it, and then we'll take the derivative, because that's what we've gotten good at, right? Hopefully. We've been taking derivatives all this time, so if we take the derivative, we should get back to where we start. Get a good practice. So x squared over 2, if you take its derivative, the 2 comes down. 2 divided by 2 is 1. Subtract 1 from the exponent, you get x, which is what we started with. X to the third over 3, this is the answer. It's the integrand, it's the antiderivative. Take the derivative, now we're trying to go backwards. The 3 comes down. Subtract 1 from it. 3 divided by 3. 3 minus 1, we get x squared, which is what we started with. Okay? But do this process, because here's the thing is, you know, smart as we are, we see things, but our brain works better when we actually do things. You know, it'll remember it better. So go backwards, forwards, backwards, forwards. And this last one, x to the minus 1, I like to write it as 1 over x because it's a little clearer for me, that we're not doing anything with the exponent. That when I integrate this, yes, we're going to get natural log, because if we take this derivative of c is 0, derivative of natural log of x is going to be 1 over x, which is also x to the minus 1. So that checks. Okay? And again, that's one where we just have to remember that's what's going on. Okay? So even the textbook says that's a good idea. And we'll go through, checks it. Okay? We're going to go through, do a few examples, calculating an indefinite integral. But again, we already know the process. We've got x to some power. We're going to add 1 to the exponent, divide by that exponent, because that's the opposite. So they give the formalized thing is you're going to integrate x to the n, add 1 to the exponent, and divide by that new exponent. And you get plus a constant, okay, because these are indefinite. If you have 1 over x or x to the minus 1, it integrates into natural log, and we talked about that. So again, I told you that first page, I covered pretty much the whole slideshow right there. And they give the alternate one. I like this 1 over x because I can spot this a lot easier than x to the minus 1. I'm tempted to add 1 to the exponent and divide by it. But if you try that, right, if you start with the x to the minus 1 exponent, what happens if you add 1 to it? You're going to get 0. What happens when you divide by 0? Oops, it's undefined. That tells you why. This is where you start to understand why the natural log's derivative is 1 over x. In fact, when they do the proof, the proof of their derivative, they use the integral, so they're kind of working from both ends. But it just is because it has to be. Okay? So that's a special case, and we're good there. So let's just look at this one. X to the 55th power, if we want to integrate it, what are we going to do? Let's just do the details. First step is to plus 1 to the exponent. Perfect. Second step is to take that new exponent and do what with it? Divide by, so 55 plus 1. So we're going to get x to the 56 divided by 56 plus a constant, and we're done. Again, come back and take the derivative of what you finished with, because remember, when you do, you're supposed to get what you started with. So the 56 comes down. 56 divided by 56 is 1. You're just going to have x to some power. Subtract 1, you're going to have x to the 55th power. That's what we started with. You see how we're able to check our answer. This is where it gets kind of cool. So this is where you're going to pick up what, you know, and some of you have been doing just fine. That's, you know, but this is where I started, because again, I took calc twice. Actually, I took two calcs. I took calc 1 and calc 2, both of them twice. And that's where it started to click for me as we go back and forth. And then we talk about derivatives of exponentials. Again, I already talked about them, but since e to the x is its own derivative, when we integrate it, it's also its own integral. Because we really did nothing. E to the x, we take its derivative, we got e to the x. So we do nothing, and when we integrate it, that's what we get. Now remember, if we have a different base, I didn't cover this because we don't do it that much, but there's this natural log of b that comes off when you take its derivative. So just a little practice. If we had b to the x, remember when we take its derivative, well, they got it over here, but you get b to the x, but then you also have to multiply by the natural log of b. Okay, so that We didn't do a lot of those, but that was the definition of anything other than base E. If it was base E, it's the natural log of E, which is 1. So since that happens, we've got to divide by the natural log of B. Okay, so again, just some things we're going to need to put in here. Okay.
B represents what?
B is any number. It's the base, so it could be like 5. Yeah, that's so if you had 5 to the x and you take its derivative, take its derivative, you're going to get 5 to the x, it's its own derivative, but then you're going to multiply by the natural log of 5. Okay, so that's why when we integrate, we have to divide by the natural log of 5 because we didn't start with it there, so we have to get rid of it. So you can, it just starts to make sense if you'll go back, forward and backward, forward and backward, forward and backward. Okay, we're almost there to the end. Well, what if we had our function was 3x squared minus 4x plus 5? How would we take the derivative of this function? Or what would be the derivative of this function?
6x minus 4.
Excellent. 6x minus 4. Derivative of 3x squared, the 2 comes down. 2 times 3 is 6. Subtract 1 from the exponent. 4x, that's to the first power. The 1 comes down, times 4. X to the 0 power, which is 1. So now, again, we've got our answers are sitting right there. What if I asked you to take the integral of 6x minus 4? Remember, these are always a derivative. We're starting with the derivative. What would we do? We know what we need to end up with. We need to end up back up there. How are we going to integrate this? What's the exponent on the 6x? 1. So again, what do we do with it? Add 1 to the exponent. Good. There we're going to see we get x squared. And then we divide by that new exponent. I'll just do it as 2. 1 plus 1 is 2. And what you're going to see is that just when we took the derivative, we could do it term by term by term. Wouldn't it make sense that we can integrate term by term by term? Well, we can, whether it makes sense or not. But yes, I think it would make sense. We don't have to prove it because we're not mathematicians. So yes. So if I got 4 as my answer, what would I have to get back? This is a little harder, but what I'm going to do is, this is really not just minus 4, it's minus 4x to the 0. So think of that. X to the 0 is actually just 1, isn't it? Anything to the 0 power is 1. So if we do it this way, we need a little bit of help. So again, we're going to do what? We're going to add 1 to the exponent and divide by that new exponent. So we're going to get 0 plus 1, which is, so let's do all of this. So 6x, we're going to get 6x squared over 2 minus 4x to the first power over 1. And then we're going to simplify. 6 divided by 2 is 3. X squared minus 4x. Oh, plus a constant because we didn't get it. And then when we look back up here, isn't that what we started with? It is. It is. So you see, we can integrate term by term, just like we can take the derivative term by term. It's kind of one piece at a time. So all those rules work the same way backwards and forwards. So again, we're introducing them, but they're really nothing new if we think about it, right? I could have 5 terms, and it's just I'm integrating each one separately. So far, we good? Okay. And that's what this thing says with funky notation. But if we're integrating basically two different functions like 3x squared minus 4x, we look at them as a sum of two functions, then we can integrate them separately. That's all it says. And again, I wouldn't use all this notation. I said, let me just do it one piece by piece, just like I've been doing derivatives, right? If I can do a derivative piece by piece by piece, I will integrate piece by piece by piece. What happened if we had a constant multiplier, right? Constant multiple rule. We had 5x to the third, right? You could think of that 5 just sitting outside. You take its derivative, that's going to be 3x squared, and then you just go ahead and multiply it. Or you just do it all in one step. Same thing is true with an integration. You can, if there's a constant, if we want to take 15x squared and we want to integrate it, again, we know what we're supposed to end up with. We can just say, okay, take that 15 out and we'll deal with it later. Let's just integrate x squared. Let's not worry about the 15. Again, what you'll do is you don't actually do this as a separate step, but you just conceptually, you just bring that along. We've already sort of been doing this, right? Integrate x squared, we're going to get x to the 3. 2 plus 1 is 3. We're going to divide by 3. We're going to put plus a constant. And, oh yeah, we have this 15 out here that we're supposed to multiply. But when we do that, 15 divided by 3 is 5. Plus some constant. And again, you should distribute the 15 to the c as well, but since c is just a general number, 15 times a general number is also a general number. Okay, so c could be anything. That's all it's saying. Make sense? Constant multiple. So anytime we got a number, we don't have to worry too much. We can just kind of ignore it. And they're just giving you some of the sum rules. So this is x to the third plus 1. Integrate x to the third. You get x to the fourth plus over 4, right? Because we always got to divide. So add 1 to the exponent, divide by it. And then when we integrate 1, again, it's a very simple one, but it's also sometimes what makes it complicated. You integrate 1, you're going to get plus x. Some of you, when you had the derivative of x, that's what, that I've seen some of it, you put 0 or something, we're not quite sure what to do with it, but it comes from when we integrate just a number, we're going to get our x. And again, remember, because this is really x or 1 x to the 0 power. If I do that, that helped me a lot to say, okay, yeah, you add 1 to the exponent, you're going to get x to the 1. Same thing down here. So just, and this is the multiplier. So we did another example. Bring the 5 outside, do your integration, then multiply, however you want to do it. So constant multipliers, they're just that. So let's look at a couple applications. Marginal cost. Marginal cost. What is a marginal cost? How did we get a marginal cost? It's a derivative of the cost function. And what does it represent? It's the cost for doing one more thing, right? That's a marginal, but it came from a derivative. So when they give us the function that's a marginal, see the word marginal, and we'll see this a lot, this is a derivative. And they want us to go back, let's see, what do they want? Find the cost function, so the total cost function, not the marginal cost function. We have the marginal cost function. We want the total cost function. So what they were asking us to do is, let's see. I have a hard time with that symbol because I want to do it backwards. 4 minus 0.001x dx. Okay, so that's what they're wanting us to do, is integrate that, get the antiderivative. So for our first step, and I like to work down, because that's what we're going to do, is when I integrate 4, what am I going to get? Remember, this is really 4x to the 0. Add 1 to the exponent. So that's x to the first power, divide by 1. There we are. Then I've got this, which is x to the first power. I'm going to add 1 to the exponent. So we're going to get x squared. And we're going to divide by that new exponent. And this minus 0.001 just kind of comes along for the ride. Okay. And then we have plus a constant. So that's pretty much it. Our function is 4x. Let's see, 0.001, half of that is actually going to be, think of this as 0.0010. Half of 10 is 5. So this becomes 0.0005. I think I got that right. And again, you could just plug it in your calculator and you'd get it, x squared plus a constant. And then what we can do is we take this piece of information. This is where we can actually find out what that constant is. Because we don't, this is a general cost function, but if you're running a business and you don't know what your fixed costs are, you're going to go do that? It might be $10,000. Make one hat for, I got to pay $10,000 rent. You know, this is your fixed cost, right? So I want to find out what it is, and they do this by telling us if we make 100 caps, the total cost will be 400. So what that allows us to do, again, we could think of this as the cost function, but when we do 100 caps, so that's 4 times 100 minus 0.0005 times 100 squared plus some constant, that we're supposed to equal 500. And notice now we got all numbers except for a c, a constant. We'll figure out what that constant is. We will know the exact function. So we're getting to this place where it's no longer indefinite, it's a definite integral. One lesson, we went from indefinite to definite. Okay. So what does this give us? Let me come up here. 500 equals 400. 0.005, so 100 squared is what, 10,000? It's yeah, 10,000, isn't it? 10,000 times 0.0005. I think that's about $5. Let me check it out. 100 squared is 10,000 times 0.0005 is $5. Yes. So that part is just minus 5 plus a constant. So that's $395 plus a constant. Subtract 395 from both sides. And we get 105. Is that right? Is our constant. So that's our fixed costs. So now we can say, hey, we know exactly what this cost function is. It is 4x minus 0.0005x squared plus 105. And I had to kind of squeeze it in there, but okay. So now you see we can actually get back, but we needed that extra piece of information. I remember doing these when I was going, why is that important? Well, that's important because that'll give us the plus c, gives us what c is. But it isn't real clear. So I could tell I knew I needed to get the integral. But I said, who cares if the 100 caps cost 500? That's how you get your c. And so then we get the exact function, and okay, fixed costs are $105. I could handle that. I'm going to make this, and now we know exactly what we're doing. But yeah, you don't want to open a business and not know, not know all the information. You got to get this, and that's where we're going. Okay, so they'll give you those. Questions on that one? No? Okay. And then again, as I do, I leave the textbook is going to. So they just did the same thing we did. They integrate it. And they use K instead of C. K for constant. I spelled constant with a C. Anyway, and then they solved and got the 105. Okay, so that's nicely written out and everything. And so that's our final one. Mostly what I'm going to do with this is it's basically the same thing. And this comes, but this is nice because it came right from the last test. In the last test, there was a question where they gave you a position function s of t equals something. And what did they ask you for? Well, it was just Monday.
Was that the one where I asked, like, compared to something?
No, they gave you a position function, and they wanted the acceleration. Remember, you had to take two derivatives to get the acceleration. That's all this is. When they give us the acceleration, we'd have to integrate twice or integrate once to get back to velocity. If you've got velocity, integrate once to get back to the position function. So, and again, this might not have a big business application. It's a physics, they'll use it, but it's the one application that we can physically see and feel and taste and experience. But the costs and stuff, it's not so much. But this one you could actually feel. So they always start having s to be the position function. And remember that what they mean by position is that tells you how much distance you're traveling over time. If you know how much distance you travel over time, that gives you a rate, that gives you a speed. Velocity is just directed, whether you're going forward or backward. So velocity is a directed speed. Okay. So we've done this before. We take the first derivative, and again, so we could do this as s prime. That's what velocity is. If we take the derivative of velocity, we get acceleration. And again, what we were doing is saying, oh, that's the same thing as taking the position function, taking its derivative twice. Okay, so it's just seeing that there's these three functions, position, velocity, acceleration, that are derivatives of each other kind of in a descending order. So when we go backwards, if they give us the acceleration, we can integrate once, we will get the velocity. If we have the velocity, we can integrate again, we can get our position. Okay, maybe we need to know how many miles our van traveled, but all we know is how much it's accelerated, so we could go backwards with this. And so this is what it's going to look like for us if you have the acceleration. Remember, that's a derivative of the velocity, so when you integrate it, you get back to the velocity. We've got a function that they tell us is a velocity function. If we integrate it, we get back to the position function. Okay. So we're told that we're going in a straight line and that the velocity is 4t plus 1. What would be the position function? All right. We're going to integrate this. That's all we're going to do. What's the integral of 4t? It's got an exponent of 1. We add 1 to that. It's going to be 4t squared divided by 2. And you'll notice when I do these, I keep the 4 there as a constant multiple, divide by 2. Okay. When we have a constant and we integrate it, it's not that it becomes 0, but what will it become? This plus 1, it becomes just the single t to the first power, right? Because that's plus 1 t to the 0 power. And then, since we're integrating, we get plus a constant. And again, just to smooth this out, 4 divided by 2, 2t squared, plus t, plus some constant. And you see why I don't like using t as a variable, because my t's and my plus signs all look alike. I'll try to make that smaller or something.
Just use a capital T.
Capital T's work, yeah. Of course, yeah. But then sometimes software, if you use a capital T and they want a little t, but anyway, but yes, it's just, okay? So that's something, if we've got velocity, we want the position, we could go back. The velocity of a particle moving along a straight line is given by this. So this is what we just did. But notice, given that the particle is at position s equals 2 meters at time t equals 1. What are we going to use that for? to get the constant. Okay, so we just integrated this. We're going to integrate v of t dt, and we saw that that was 2t squared, right? Becomes t squared divided by 2 plus t plus a constant. And then we know that this is, when we integrate, that we're getting a position function. And we're told that s is 2 when t is 1. So we plug in 1 for t plus a constant. And we know that that has to equal 2. And that will allow us to solve for the constant. And you'll see in the homework they've got a couple problems like this. 1 squared is 1 times 2 is 2 plus 1 is 3 plus a constant equals 2. So we get 3 plus a constant equals 2. Subtract 3. We get the constant is negative 1. 2 minus 3. So so our position function will then be 2t squared plus t minus 1. And notice we don't have to have a plus c because we figured it out. You good? Making sense? The hardest part is just remembering to do everything backwards, right? Adding 1 instead of subtracting 1. Spent so much time remembering to, and that's the problem, is you just got to, what am I doing? Am I taking a derivative or am I integrating? Which way am I going? Got to keep track of that, and then you'll be just fine. And they're working through it, and again, they just did nice printed version of what I just walked through, right? Solve for, we know that at time, at 1 second, it's 2 meters, and so we end up with that. Where are we? Oh, we got a few more minutes. The last homework problem kind of gets into this. Galileo's dropping something or throwing something off of a building and stuff. So we got this constant of gravity, right? So freely falling body experiencing no air resistance. Where's that going to happen, right? So much pollution in our air. Zero initial velocity. Find an expression for the velocity v in terms of t. So notice they're giving us the rate of acceleration. Freely falling body accelerates downward. So if it's going downwards, what direction or what sign should we have? We could go with either one of these, either 32 feet per second squared. And remember, those are the units for acceleration. Velocity would be feet per second. So again, what we're doing, it's a constant. So we're integrating 32. What should we use? dt? Why not? And this is going to give us velocity. But the 32 is going down, so what sign should I put on the 32? Make it positive or negative? Negative, right? Because it's coming down. Just standard procedure. So when we integrate it, we're going to get negative 32t plus a constant. And this is going to be our velocity. Make sense? If you want to do metric, you would do the same thing with 9.8. You'd have 9.8 t. It's just your units would be meters instead of feet. So just make sure you're using the right things, right? Same meters. But yeah, you could get different things that this is going to be. And our units here are now going to be feet per second because we integrated and we've got velocity, so it's not seconds squared, it's feet per second. So that's kind of sometimes how you can tell the difference between acceleration and velocity. And then when we get to position function, the seconds will go away and it'll just be feet. So we know we just got a distance that's been covered. In fact, while we're here, could we get the position function? That's going to be the integral of the velocity function. So we're going to integrate negative 32 t plus c. So when we integrate negative 32t, what do we get? We add 1 to the exponent, and then we're going to divide by that new exponent, right? 32 divided by 2, you get negative 16 t squared. When you integrate the constant, you're going to get plus some constant times t plus another constant. That's why it's usually, when you do these, you get some information so you can find the constants as you go. Otherwise, you end up with a lot of unknowns, right? But this is how we would do it. In your algebra class, or even early on, anytime they have like something that's a ball's thrown in the air, you'll always see this minus 16t squared, because that's the force of gravity that's affecting the position function, right? Whenever you have how high is the ball, that you always see this negative 16t squared, because it comes from the constant of acceleration due to gravity, which gives us the velocity, which gives us a position function. Okay, so now you start to see how all this stuff is connected. And again, they're just backing up a little bit. If this is our acceleration, they're just nicely putting what I've written up. We integrate acceleration, we get velocity, so negative 32t plus a constant. And then they give us some information that at time 0, the velocity is 0, so we can plug that in. Well, 0, that means the constant 0. So this is your standard velocity function for something that hasn't been moving. If it was already moving, it would already have some speed. We would just add that to it. We're going to see that that's what happens. Okay. And again, here, they just give us these formulas. And again, it's sort of what we derived, but velocity will be negative 32t plus whatever, if it was already moving, whatever the initial velocity was, right? That would add to it. Or subtract to it if, that's like they throw a ball in the air. It's going upwards instead of downwards. Okay. Then the position function becomes negative 16t squared, whatever that initial velocity is, times t plus some beginning place. And then these are in metric. Okay, so you can kind of use these, and if they're not too hard to memorize, so you won't, I don't know that they will be given to you on a test if we had something like this, but you could derive them, but they're just, as long as you know that negative 32 feet per second, that's acceleration due to gravity, all of these come from that. Okay, but if you have it, you could also, and that's what they do in physics. They don't do a bunch of calculus each time they're going to do this. They remember these because gravity on Earth doesn't change. Now, if you're on the moon, it'd be different, but gravity on Earth will always be this. So you just memorize these and use them. And so if a ball is thrown up at 2 feet per second from a height of 200 feet, then its velocity and position after t seconds are. Well, velocity, remember, is negative 32t plus the initial velocity. And the initial velocity is 2 feet per second, and it's being thrown upward. So is that a positive or a negative? Positive. Okay. So we just remember this formula. We don't have to do all the calculus behind it. It's going to be negative 32t plus 2. That's the velocity function. The position function, again, just kind of, if we go back, we can pick it up here. It's always going to be negative 16t squared. The initial velocity times t plus its initial position. Well, they gave us that. So again, we don't have to do too much because we've already done it. This is repetitive. And then the initial velocity was 2 feet, 2t. Notice if you take 2 and integrate it, you'll get 2t. Take negative 32t and integrate it, you get negative 16t. And then what's the constant? Well, we started at 200. They gave it to us here. Okay. So this one, especially as business majors, I wouldn't try to do the calculus to get to integrate all of these. You could if you want, but just go back and take that slide, use those formulas. And again, I think there's just one homework problem at the very end, talks about Galileo, but you can apply them directly. Okay? Because even in Galileo's time, acceleration due to gravity was negative 32 feet per second. Okay? But this is where we start doing things backwards. It's a good time to start integrating what you've already learned. And again, no matter where you're at, if you can continue doing the work, the homework, learning from it, and you can pass the final, you will at least pass this class. Okay? So pass that final, regardless of it. Now, some of you, if you've been doing well, what it does is you could actually fail the final and still pass the class. But you probably won't fail it because you've already been doing well. But everybody who's still engaged and still comes in and takes that final, I guarantee you, if you can pass that final, you will pass the class. It's not the syllabus, but you got to trust me.
I think this is the hardest thing.
What's that?
I think this is the hardest thing we've done so far.
It's because it's new, but yeah, it is. Thank you.